Good afternoon. This is Mrs. Boland with the University of West Florida. Today we're going to be talking about hypothesis tests, and this starts our Mod 8. So, what are hypothesis tests and why do we perform them? We think a cola company is not filling 12-ounce cans with 12-ounce cans or 12 ounces of soda. Suppose we take a sample of 100 cans of soft drinks under investigation. We find out that the mean amount of soda in these 100 cans is only 11.89 ounces. Based on this result, can we state, on average, all such cans contain less than 12 ounces of soda, and that the company is lying to the public? Not until we perform a test of hypothesis can we make such an accusation. The reason is that the mean of the 11.89 ounces is obtained from a sample. The difference between 12 ounces, the required amount for the population, the legal amount, and 11.89 ounces, what we observed in the sample that we took, may have occurred only because of sampling error. Another sample of 100 cans may give us a mean of 12.04 ounces. Therefore, we make a test of hypothesis to find out how large the difference between 12 ounces and 11.89 ounces really is, and to investigate whether or not this difference has occurred as a result of chance alone. Essentially, what we want to determine is, did the 100 cans that were randomly selected show a true problem that exists, that there's not 12 ounces of cola on average in those cans that are marked 12 ounces of cola? Or was it just a random sample that just happened to be very rare, that we ended up with a mean below the true average, below the true population mu of 12 ounces or something higher? That's what we have to determine. What is the true situation going on here? So we have two hypotheses. We're going to leave the cola example for just a moment, and then we'll come back to it. So consider a non-statistical example of a person who has been indicted for committing a crime and is going to be tried in our courts here in the U.S. Based on the available evidence, the judge or jury will make one of two possible decisions. The first one is that the person is not guilty. The second one is the person is guilty. Those are really the only two outcomes. At the outset of the trial, the person is presumed not guilty. The prosecutor's efforts are to prove that the person has committed the crime and hence is guilty beyond any shadow of a doubt. In statistics, the person is not guilty, that phraseology there is called the null hypothesis. And in statistics, the person is guilty, that phraseology, that logic, is called the alternative hypothesis. The null hypothesis is denoted by H naught. I call that H naught. You see the zero, it's a sub-zero, okay? And the alternative hypothesis is denoted by H sub 1. So H sub 0 is the null, okay, not guilty. H sub 1 is the alternative, the person is guilty. Sometimes you will see the alternative hypothesis denoted with a sub A instead of a sub 1. Okay, so sometimes you'll see a sub A here for alternative as opposed to 1. In the beginning of a trial, it is assumed that the person is not guilty. Okay, that's the way we work here in the United States. The null hypothesis is usually the hypothesis that is assumed to be true. Okay, so just like we assume that the person is not guilty to begin with, we're going to assume the null hypothesis is also true. The two hypotheses for the court cases are written as follow. Notice that there's a colon after the null hypothesis and alternative hypothesis notation. So the null hypothesis is the person is not guilty. The alternative hypothesis is the person is guilty. Okay? In a statistics example, the null hypothesis states that a given claim or statement about the population parameter is true. Reconsider the example of the soft drink company claim that on average, its cans contain 12 ounces of soda. In reality, this claim may or may not be true. Okay, it's one or the other, right? It's either true or it's not true. However, we will initially assume that the company's claim is true. That is, the company is not guilty of cheating and lying. That's what we're going to assume. To test the claim of the soft drink company, the null hypothesis will be that the company's claim is true. Okay, so we're going to say our null hypothesis is that mu does equal 12 ounces of cola. The company's claim is true. That's where we're going to start. Let mu be the mean amount the soda in all cans. Okay, so we're going to let mu equal what is claimed to be true. The company's claim will be true if mu equals 12 ounces or more. Okay, the company is in good shape as long as they're not putting less than 12 ounces of soda in those cans. They only have a problem, a legal problem, if they're putting in less. If they put in 13 ounces, legally they're fine because they put on the can that they have 12 ounces of soda. Financially, they're not making a good decision because they're actually throwing their profits away by putting in an extra ounce. But they cannot be sued for putting in less if they're actually putting in 13. It's just not a wise business decision, okay? But the reality is they're not going to get in trouble if they have 12 ounces or more in each can. Thus, the null hypothesis will be written as, again, H naught, colon, mu equals 12 ounces. This is what has historically been true. This is what the company claims is true, okay? So just like you're innocent until proven guilty, we're going to assume that they actually have 12 ounces of cola in their cans until we can prove beyond a shadow of a doubt that they do not have 12 ounces of soda in their cans, that in fact they have less. Okay? In this example, the null hypothesis can also be written as mu is greater or equal to 12 ounces. Remember up here, we said that the company's claim will be true if mu is equal to 12 ounces or more, okay? They won't get in legal trouble if they're actually putting 12.5 ounces consistently in their cans of cola, or if they're putting in 13 ounces or whatever, okay? They'll only get in legal problems if they're taking and falsifying how much they're putting in by having less than the amount that they state on the can. So we can write the null hypothesis as mu is greater than or equal to 12, just like we can write it just like here, mu is equal to 12. Either one of these statements is perfectly acceptable and fine and the same. Okay, because the claim of the company will still be true if the cans contain on average more than 12 ounces of soda. The company will be accused of cheating. So the company will be accused of cheating only if the cans contain on average, that's the important part right there, less than 12 ounces of soda. However, it will not affect the test whether we use an equal sign or greater than equal sign, as in here or here, in the null hypothesis, as long as the alternative hypothesis is a strictly less than. Okay, so the alternative hypothesis must be a strictly less than. The alternative hypothesis can never have an equal in it. Okay, it's just not going to happen. If you put that in, it is wrong. The alternative hypothesis in our statistics example will be that the company's claim is false and the soft drink contains on average, again, that's the key part, less than 12 ounces of soda. That is, mu is really less than 12 ounces. The alternative hypothesis will be written as H colon mu is less than 12 ounces. The company's claim is false. That's the English translation of what you see written right here. We have two types of errors that can occur. We need to understand what those errors are, and we need to decide which error we're going to control, okay, and which one we are not going to influence as much. So we know that the court's verdict is not always correct. Sadly, that's just true. If a person is declared guilty at the end of the trial, there are two possibilities. The first one is the person has not committed the crime, but is declared guilty. The second error is the person has committed the crime and is rightfully declared guilty. Okay? So again, if at the end of the trial, the person is declared guilty, either the person is guilty but did not commit the crime, was declared guilty but did not commit the crime, or was declared guilty and did commit the crime. Those are the only two possibilities, right? Okay. In the first case, the court has made an error by punishing an innocent person, okay? Because the first case was the person was declared guilty but did not commit the crime. So in that case, the court made an error by punishing an innocent person. In statistics, this kind of error is called a type 1 error or an alpha error. Okay? In the second case, because the guilty person has been punished, the court has made the correct decision. So in the second decision here, the court made a correct decision. No mistake was made. We're going to look at the chart here, and the type of errors that we have in statistics, okay? So in the first scenario here that we just looked at, the person did not commit the crime, but is declared guilty. That is a type 1 error or an alpha error. The court's decision, the person is guilty. The actual situation, what's reality, the person is not guilty. That is the type 1 or alpha error. This particular error we want to minimize. That's one of the reasons why in the United States we have the court system set up the way we do. It says you are innocent until you are declared guilty. That beyond any shadow of a doubt, you are declared guilty. The court system in the United States would rather err and let a guilty person free than to lock up an innocent person. That is the exact same thing here with our type 1 error or our alpha error. That would be saying that we do not want to falsely accuse the soda company of putting in less than 12 ounces of soda in their cans. Okay? We would rather miss the fact that they really are putting in less than 12 ounces of soda in their cans than to declare that they are putting in 12 ounces putting in less than 12 ounces when the reality is they're not. Okay? We would rather miss the fact that they really are cheating the customers and declare that they aren't cheating the customers than to falsely accuse a company of cheating customers because we had a study that showed that they were putting in less, okay, than when they really are not cheating the company. Okay, it's very important that you understand this. So we want to always control what's called a type 1 error. So the type 2 error, the beta error, occurs when the court's decision is the person is not guilty, but in reality, the person is guilty. Okay? So the court's decision would be that we are not putting in less than 12 ounces of soda in each can. But reality, the company is knowingly putting in less than 12 ounces of soda in the can. So let's continue to read. In our statistics example, the type 1 error, which is the alpha, will occur when H naught is actually true. The cans do contain, on average, 12 ounces of soda. But it just happens that we draw a sample with a mean that is well below 12 ounces. And we wrongfully reject the null hypothesis. Okay, we reject the null hypothesis and conclude that the alternative is true, meaning that the cans have less than 12 ounces of soda in them. That is when a type 1 error occurs. The value, alpha, is called the significant level. The significant level of the test. It represents the probability of making a type 1 error. In other words, alpha is the probability of rejecting the null hypothesis, H naught, when in fact it is true. Or another example would be the court ruling that the person is guilty when in fact the person is innocent. Okay? That is the type 1 error. And that's what we're going to focus on whenever we do hypothesis testing and try our best to minimize that occurring. The size of the rejection region in a statistics problem of a test of a hypothesis depends on the value assigned to alpha. In a test of hypothesis, we assign values to alpha before making a test. Extremely important. This is always done before. Although any value can be assigned to alpha, the commonly used values of alpha are 0.01, 0.025, 0.05, and 0.1. Usually the value assigned to alpha does not exceed 0.1 or 10%. Now suppose that the court trial case, the person is declared not guilty at the end of the trial. Such a verdict does not indicate that the person has indeed not committed the crime. Again, suppose that the court trial case, the person is declared not guilty at the end of the trial. Such a verdict does not indicate that the person has indeed not committed the crime. It is possible that the person is guilty, but that there simply was not enough evidence to prove the guilt. Consequently, in this case, the situation, again, there are two possibilities. The first one, the person has not committed the crime and is declared not guilty. That would be the correct situation. That would be a good situation. The second situation is the person has committed the crime, but because of lack of evidence, is declared not guilty. Not a good situation, but it does happen. In the first case, the court's decision is correct, meaning option 1 up here. But in the second case, the court has committed an error by setting a guilty person free. That would be option 2. They just didn't have the evidence to prove beyond a shadow of a doubt that the person did the crime. In statistics, this type of error is called a type 2 error or a beta error. Okay, so now we have an alpha error and a beta error, or type 1 error and a type 2 error. The two types of errors that occur in test hypothesis depend on each other. They're not independent. We cannot lower the value of alpha and beta simultaneously for a test of hypothesis for a fixed sample size. So we have a fixed sample size. We cannot change alpha without affecting beta. It just cannot happen. Lowering the value of alpha will raise the value of beta, guaranteed. And lowering the value of beta will raise the value of alpha. Again, this is for the fixed sample size, but if you try to lower alpha, you're going to raise beta. And if you lower the beta, you're going to raise alpha. So you're going to increase the probability of a type 2 error if you lower the probability of a type 1 error. Or you will increase the probability of a type 1 error if you lower the probability of a type 2 error occurring. They are directly influenced by each other. They are not independent. However, we can decrease both alpha and beta simultaneously by increasing our sample size. That's one thing we can do to hopefully to directly influence the probability of alpha and beta, and decrease them is by increasing our sample size. So we've talked a lot about the concept of hypothesis testing. We've talked a lot about what a hypothesis test is. We have our notation, H0, H1. H naught being our null hypothesis, which is where we put in our historically known data, or what has been historically known in the past to be true. H1, which is our alternative hypothesis, is going to state what we think the new situation is. We have two types of errors, type 1, type 2, an alpha and a beta. We're going to choose to control our alpha, which means I would rather let a person go free if they're really guilty than to put an innocent person behind bars, okay? In other words, I would rather miss the fact that the process has changed and the mean has really changed than to conclude falsely that the mean has changed on a production when it hasn't changed. Okay, we have three different scenarios when it comes to hypothesis testing. Our first one that I want to discuss is called a two-tailed test. We have a two-tailed test when we have H naught is equal to, when we have mu is equal to a particular value that we're just going to call mu naught. And then we have our alternative, which says that mu is not equal to a particular value called mu naught. And we can draw our standard normal curve. We'll put 0 in the center because we're going to standardize our mean, and we're going to be on the standard normal. We're going to be working on the z distribution initially. Eventually we will get to the t, but right now we're going to be working on the z. And then we have our critical values, which are going to be a negative z star and a positive z star. Okay, and in the very center right here, it's going to be our fail to reject. Fail to reject. A lot of my students will put in here do not reject. I prefer fail to reject because that's what's going on. Change it to however you need to make sure you understand what's going on here. And then right in here, we have half of alpha coming in here and half of alpha coming right in here. And these would be where we reject. Okay, so we reject. We reject if we end up with a value here, and we reject if we end up with a value here. So this is a setup of essentially the playing field, okay? This is the initial setup. And now, once we have this, what we're going to do is we're going to say that I'm going to go out and collect data. I'm going to calculate a mean, and I'm going to see how far away is the mean of the sample from the prior known population mean, okay? Is it within my critical values, which would be right in here? Would be right in here. Is that where the sample mean falls once it's been standardized? Or does it fall in the tails? Does it fall in the tails over here? Okay, so when I have a does not equal sign in my alternative hypothesis, it means that I will be concerned if my new mean, if I see a shift that's an increase or a decrease. It doesn't matter. Either one of these are a change, okay? It's different from mu. It's different from my historical data. And therefore, I can say that a change has occurred. So whenever you see a does not equal sign, that is a two-tailed test, okay? So we have does not equal means a two-tailed test, okay? Words for you to observe as you're reading a word problem would be the word different, or change. There's other words too, and I'll point them out as we go along. But those are the words that I'm thinking of right off the top, okay? So when you see, has the mean changed or is the mean different from a particular value, you're looking for a two-tailed test, in which case alpha is going to be split on each side, just like our confidence intervals, okay? We want to control as much as possible. We want to minimize as much as possible a type 1 error. And so we want to set our alpha level to minimize the probability of a type 1 error from the get-go. Alrighty, and when we're dealing with a two-tailed test, which means if we've had a change of something getting smaller or something getting larger, okay, a change in either direction is a change, which would be something different than historically known, okay? In which case we put half of alpha in one area, half in the other. Now we have a couple of other scenarios. We have what's called a one-tailed test. In our one-tailed test, so this is a two-tailed test. And then we have our one-tailed test. And that is, if we have H naught is that mu is greater or equal to a particular value, and H sub 1, our alternative, is that mu is less than a particular value. In that case, what we have is we have something very similar to what we had over here, where we standardize the mean, it's in the center. You see this right here though? That arrow, okay, it's a less than sign. It is pointing in the direction of where the alpha is going to be, the area that we're going to be concerned about. And so our critical value is going to go on the left-hand side, and it's going to be a negative value, okay? So our fail to reject is all of this area, and our rejection area is right here. And this is where we're going to put all of alpha in this part. And we're only concerned about if the sample mean is so far away from the historical data, below, only if it's below. If it's greater, we don't care, okay? But if it's significantly enough below, now we're going to say the process has changed and we are now putting in less, maybe less soda into a can than what we have been previously. This is a one-tailed test. We have another one-tailed test, though, that we also need to be aware of, and it looks like this. It is when we have, let me highlight this right here. All of this is together, okay? And then we have H naught, where mu is less than or equal to mu naught. And then we have H1, which is when mu is greater than mu naught. Again, which direction is the greater than sign pointing? It's pointing to the right, okay? So this tells you it is a right-tailed test. And our right-tailed test looks like this. Very much like the others, okay? And we're going to put our critical value, though, on the right. And we're going to have Z star right here. And we're going to have our fail to reject, or fail to reject over here. And then we're going to have our alpha, all of it, right here, okay? And this is reject. We're not cutting alpha in half because we're putting the whole area at the greater side, okay? So in the right-hand side, so this is a right-tailed test, a right-tailed test. And this is when we're going to be concerned about a shift to the right, something being increased, okay? And both of these, this is also another one-tailed test. Okay, so there you go. Now, we have our two-tailed test up here, and that means we split the error, the alpha, into each tail, okay? And that occurs when we say cannot equal, okay? When it cannot equal is if it's less than or greater than either scenario, it's not equal, therefore we have a two-tailed test. We have a one-tailed test where we say that the mean has shifted and it's significantly less than what it used to be. That's a left-tailed test. Okay, let me write that in here. Left tail. And you know it's a left tail test because all of alpha is in the left tail. Then we have the other scenario, which is also a one-tailed test. Okay, this is also a one-tailed test, but it's concentrated on the right. So this is a right tail test, okay? And we're putting all of alpha to the right. And we're only interested if the process has changed so that the true population parameter has shifted and increased to the right, okay? Remember that when you're looking at a one-tailed test, all you have to do is look at the alternative hypothesis to determine which tail alpha should go. Alrighty, so let's do an example and see if this helps clarify a little bit of what we just went over. So we have a two-tailed test. According to the U.S. Bureau of Census, the mean family size in the U.S. was 3.16 in 1992. A researcher wants to check whether or not this mean has changed since 1992. The key word here is actually change, okay? That is the key word. The mean family size has changed if it has either increased or decreased during the period since 1992. This is an example of a two-tailed test. Let mu be the current mean, okay, of the family size for all families. The two possible decisions are, 1, the mean family size has not changed, that it is still mu equals 3.16. Option 2, the mean family size has changed in that it is not mu equals 3.16. Those are the only two options, okay? So we're going to write the null and the alternative hypothesis for this test, okay? Again, the key word here is changed. Another key word for not equal to and a two-tailed test would be the word different. We write H naught as mu is equal to 3.16. Our alternative is mu is not equal to 3.16. Now, let's draw a picture of what this looks like. So we're going to have our raw data picture right here, and then right below it, our standardized picture right below. In the very center of our raw data, we have 3.16. In the center of our standardized, we put 0. What we're going to calculate is some critical value on our z, and it's going to be negative z star and positive z star. I have a negative and a positive because I have a two-tailed test which says not equal. It says that if I have data way down in here or way up in here, then I know that the new situation is different than what was previously known, okay? So in the very center, we have fail to reject. And right in here in the very center, if we find that our sample data, once we standardize it, is in the green area, then we fail to reject, and we're going to say we don't find that there's a change, okay, from our historical data. only if we cross our line, this line here or this line right here, are we going to reject. And the amount of area in here, because it's a two-tailed test, is half of alpha, and we will reject. And over here is the other half of alpha, and we will reject. Okay, so that is our image right here of what we're going to have. You can draw your other one right up here, and we can put right here and here, and we could calculate whatever this x value is, the error here and the error here, and we could draw the exact same picture once we have our error calculated about the mean here and how much of a deviation we were going to have. We could put actual numbers there. But this picture right here is what I really want you to draw. 100% of the time, this represents this right here. Okay, and that's what I'm going to be looking for. I'm going to be looking for your critical values. I'm going to be looking for your mean in the center. I'm going to be looking for your half alpha if it's a two-tailed test in each end. And then the other thing we're going to be looking for, which we haven't quite gotten to yet, is going to be what's called the test statistic and the p-value. And we will add those to this picture, okay, once we get to those. But let's go ahead and learn how to draw two more pictures, both of those one-tailed test. So this is a left-tailed test. A left-tailed test. Reconsider the example of the mean about the amount of the soda can, being the soft drink cans produced by a company. The company claims that these cans, on average, contain 12 ounces of soda. However, if these cans contain less than the claimed amount of soda, then the company can be accused of cheating. Suppose that a consumer agency wants to test whether the mean amount of soda per can is less than 12 ounces. The mean amount of soda per can is less than 12 ounces. So we have some consumer agency that wants to test this. Note that the key phrase this time is less than, okay? So this less than is the key phrase. And this indicates that we have a left-tailed test. Mu will let mu be the mean amount of soda in all cans. Okay, that's your population. That is going to be your 12. So we have two possible decisions in this situation. The first one is the mean amount of soda in all cans is not less than 12 ounces, and that is that mu really equals 12 ounces of soda in each can. The second option is that the mean amount of soda in all cans is less than 12 ounces. Thus, mu has really changed and is now less than 12 ounces. Those are the only two possibilities. Either our parameter mu is 12 ounces or more, or it is less, period. Those are the only two options. So we're going to write that as the null and alternative hypothesis for the test are written as H naught. The null hypothesis, mu equals 12 ounces, okay? H1, mu is less than 12 ounces. Those are our two possibilities. If you watch some of my older videos, and I'll probably even do it in this video possibly, remember that H naught, where mu equals 12 ounces, could also be written as H naught, where mu is greater or equal to 12 ounces, okay? It just has to be the opposite of the alternative, okay? It can be strictly equal to, or it can be written as greater or equal to, okay? It has to have that equal to, though, okay? Both of these null hypotheses mean the exact same thing. Both are 100% correct. So we can put mu equals 12 in the center, and it says right here that I am concerned that we have less than. It's only a problem if we have less than 12 ounces. So there's going to be some value here. What this value is, I do not know, okay? But I'm going to put it down here also, and this is going to be a left Z star, and this is a critical value, a z critical value, and right here is just going to be your error below the mean. My computer's getting hot, it's having trouble keeping all my lines, and then in the very center is going to be mu. Right here is our fail to reject area. So this is our fail to reject, fail to reject, and then right in here we're going to put all of alpha. All of alpha goes right in there, okay? All of it, okay? And this is where we're going to reject this area in here. And we're going to find pretty soon a test statistic. And if the test statistic is plotted in the fail to reject area, we fail to reject the null hypothesis, okay? We don't ever say that we accept the null hypothesis. We just say we fail to reject the null hypothesis, okay? We can say that we reject the null hypothesis and conclude the alternative, but we never say that we accept the null hypothesis. And then in here is our rejection area. So this is a left tail test. Remember that our tail right here, or the sign right there, lesson, points to the left. Therefore, I know it's a left tail test. Always pay attention to that. We have one more example here, and this is the right tail test. It says, according to the U.S. Bureau of Census, the mean income for all households in the U.S. was $39,020 in 1992. Suppose we want to test if the current mean income of all households in the U.S. is higher than $39,020. The key phrase in this case is higher than. Okay, you have to learn how to read the word problems and pick out the important words that tell you what we're testing. So in this case, it's higher than, which indicates that it is a right-tailed test. Let mu be the current mean income of all households in the U.S. The two possible decisions are: 1, the current mean income of all households is not higher than $39,020, and that would be represented as mu is equal to $39,020. Option 2 is the current mean income of all households is higher than $39,020. We write the null and the alternative hypothesis for this test as H naught is mu is equal to $39,020. The current mean income is not higher than $39,020, or that the mean income is higher than $39,020, okay? So let's draw a picture that represents this. Again, we have a one-tailed test. We know it's a one-tailed test because we have a strictly greater than sign, and it points to the right. Therefore, we know that we are interested if the shift has greatly increased to the right of the mean. Now we're going to find a critical value, and that critical value is z star. And over here, it's just going to be the error above the mean. In this case, we're going to put all of alpha right in here. And here we're going to write our fail to reject, fail to reject. And here we're going to put alpha. And so if we end up with a test statistic in here, we're going to fail to reject H naught. Okay, we're just going to say we fail to reject H naught. And same within here. Okay, because these are mirror images of each other. Okay, one's got standardized data, one's got raw data. That's the only difference. And then if we end up with a test statistic in here in the right-hand tail, then we will reject H naught and conclude the alternative is true, that in this case the mean income has increased and is now greater than $39,020. Okay, and again, this is a one-tailed test. It is a right-tailed test because our error is in the right tail. Okay, And all of alpha is in one tail. So it's a one-tailed test. It's greater than, remember, this points to the direction of the tail that we're interested in. And so it's pointing to the right. And so we know we have a right-tailed test. So here is a summary. So we have a two-tailed test. That's when we have an equality sign in the null hypothesis. A left-tailed test, we will have an equality sign in the null hypothesis, or greater than or equal to. We have to have that equal to sign always in the null hypothesis, okay? And if it's a right-tailed test, it's going to be equal to or less than or equal to. Either one of these is fine in these scenarios, okay? For the two-tailed test, the inequality sign for the alternative hypothesis is not equal to. For a left-tailed test, it's always less than. And if we're talking about a right-tailed test, it's always greater than, okay? The rejection region for a two-tailed test is in both tails. The rejection region for a left-tailed test is always in the left tail. The rejection region for a right-tailed test is always in the right tail. So make sure you kind of know this, maybe take a picture of it, and so that you can reference this as you go through. It'll help you understand the material better and get the problems right sooner than later. Okay, here are the steps to performing a hypothesis test. Write them down. Take your phone out, grab a snapshot, whatever you have to do, but make sure you have these written down on an index card or someplace where you can constantly look at them, so that as you're doing your problems, you do them correctly each time. Therefore, they become second nature to you, and on the exam and in future application in real life, you'll understand what needs to be done, and you won't forget the order of doing the hypothesis test. So, steps to performing a hypothesis test. A statistical test of hypothesis procedure contains the following, it should be 7 steps. I updated this to include 2 other steps, so we'll make this 7 steps, okay? So, number 1, state both the null and the alternative hypothesis. You got to know what you're testing, right? If you don't know what you're testing, you can't perform a test. So, number 1, state what you're testing. Number 2, determine what distribution you're going to be using. Initially, for this lecture, we're going to be using the standard normal Z only, but we're about to get to the t-test, okay? You're going to differentiate which test you're going to use, just like you did on the confidence interval. If you know your population standard deviation, you're going to be using Z. If you don't know your population standard deviation and you have to use your sample standard deviation, you're going to be using T. If you are working with your proportion test, it's going to be Z. So the rules that you learned in Mod 7 for your confidence interval will apply straight forward to Mod 8 with no changes concerning how you determine which distribution to use. Step 3, determine your critical value. This gets a little bit more complex. If you understand your alpha and the pictures, you won't have any problems at all. Determine the rejection region, the non-rejection regions, by drawing a picture that includes mu and the critical values, okay, which includes mu being equal to 0 because it'll be on a standardized picture. So just like the pictures I was just showing you. You're going to calculate the test statistic. We haven't gotten there yet, but we're about to. Then you're going to plot that test statistic on the picture that you did in step 4. And then based on that picture, you're going to make a decision. Okay, so let's get busy learning how to actually do a hypothesis test. The TIV telephone company provides long-distance telephone service in an area. According to the company's records, the average length of all long-distance distance calls placed through this company in 1993 was 12.44 minutes. The company's management wanted to check if the mean length of the current long-distance class is different from 12.44 minutes. A sample of 150 such calls was placed through the company, produced a mean length of 13.71 minutes. Use the population standard deviation, 2.65 minutes. Also use a significant level of point alpha equals 0.5, 5%. So using the 5% significant level, can you conclude that the mean length of all current long distance calls is different from 12.44? That's our question, okay? As I read through the problem, I highlighted what I wanted you to key in on as important information, okay? We were given originally that the average length of all long distance calls placed through this company in 1993 was 12.44 minutes. That's going to be our mu. It says the company wants to check to see if the mean length of the current long distance calls, this should be calls, is different from 12.44 minutes. Different, okay? It could be greater than, it could be less than. I just want to know if there's a difference. Because there's a difference I'm testing for, that tells me I'm doing a two-tailed test. A sample of 150, N equals 150 such calls placed through the company produced a mean length, X bar, of 13.71 minutes. Population standard deviation, sigma, is 2.65. Using the 5% significant level, that tells me alpha is 0.05, can you conclude that the mean length of all current long distance calls is different from 12.44? Okay, so here we go. Let's write down everything that we also learned as we went through and read everything. It says that mu is 12.44. We know that a sample was taken where N equals 150. We found that in that 150, that X bar is equal to 13.71 minutes. It says our population standard deviation, sigma, is equal to 2.65 minutes. Then it says using a 5% significant level. This tells me that alpha is equal to 0.05, okay? Level, can you conclude that the mean length of all current long distance calls is different from 1244? Okay, so I often write the alternative hypothesis down first and then write the opposite for the null, okay? Because it says using using a 5% significant level, can you conclude that the mean length of all current long distance calls is different from 12.44? So that's telling me my alternative hypothesis is, can I test that mu is different, not equal to 12.44? So then I know my null hypothesis is that mu is equal to 12.44. That's what that tells me. Then it says select the distribution to use. I'm going to be on the Z distribution, standard normal, because sigma is known. Okay? Now it says determine the critical value. The critical value, in order to do that, I kind of start working on step 4, okay? So step 4 looks like this. I draw a picture of the standard normal with mu being 0 because that's on the standard normal is in the center. I have a two-tailed test because I have a does not equal to. So that means I'm going to have a negative Z star and a positive Z star, okay? So negative Z star, and I'm going to have a positive Z star. Here's going to be my fail to reject, okay? And then in here is going to be half of alpha, and in here is going to be half of alpha. Well, alpha is equal to 0.05. So half of alpha, half of 0.05 is equal to 0.025. So right in here is 0.025, 0.025. That tells me that right in here I have 0.95 of the area. Do you all agree? 0.95 plus 0.025 plus 0.025 equals 1.0. 100% of my area under the curve is now accounted for. So in here, I fail to reject, okay? In here, I reject. Drew a little bit over on that one, but that's okay. All right, what I don't know yet is step 3. That's my z star. So I need to find a z star that corresponds to 0.025 in my standard normal tables. So I brought up my standard normal tables. In my tail over here to the left, I need 0.025. So I'm going to scroll. I'm going to look for 0.025. It's right here, negative 1.96. Okay, so 0.025 right here is going to correspond with a z value of negative 1.96. So I'm going to come back in here, and I know that my critical value is going to be equal to negative 1.96 and positive 1.96. When it says determine my critical value, z star is going to be equal to positive and negative 1.96. Okay? And I like to take and use my picture to help me identify it by drawing everything out. And so step 3 and 4 are kind of done at the exact same time. Always draw a picture, okay? Now I know the rules of the game. I'm going to go out, I'm going to do a sample, in this case, of 150 calls. I'm going to calculate their mean. Their mean is 13.71. I'm going to standardize that value, and I'm going to find where that standardized value is on this number line. Is it in the green area? If it is, then I fail to reject the null hypothesis, and so I will conclude at this time that there is no change, or that there's not significant statistical evidence to conclude that there is a change. If it's in the red area, then I'm going to say, wow, I've got enough statistical evidence to conclude that the mean is no longer 12.44, but that it has changed. I'm not going to give you a value that it has changed to. I'm not even going to necessarily conclude that it has increased or decreased. I'm going to say that it has changed. And then I'm going to say what the statistical study, the evidence indicates, but I cannot conclude anything other than that it has changed. Okay, so the next thing we need to do is calculate our test statistic. And this is what I said we were going to be working on, but we haven't gotten to yet. This is no different than what we've been doing for our confidence intervals. So we come in here and we're going to calculate our test statistic, which is going to be z, but not z star, it's just z. And that is going to be equal to x bar minus mu divided by sigma divided by the square root of n, just like what we've been doing for our confidence intervals. And we're going to plug in our numbers. And so we have our 13.71. So it's 13.71 minus 12.44 divided by 2.65 divided by the square root of 150. And we're going to plug this in to our calculator. And I'm going to go ahead and bring this up again just to make sure that everybody's using their calculators properly. And we're going to turn this on, clear it off. So open up parentheses and put 13.71 minus 12.44 parentheses divide, open up parentheses, so we have our order of operation correctly, 2.65 divided by the square root of 150. Come out from underneath the radical, close that parentheses, hit enter. And so our test statistic is 5.87. So 5.87. 5.87. So I've calculated my test statistic, which means I've found that my mean of 13.71 minutes, okay, is more than 5 standard deviations above mu. It's very significant. Then it says plot this on this picture, okay? So we plot this 5.87. It's going to be way out here somewhere. 5.87. It's going to be way out here in the rejection area, okay? And then it says make a decision. Well, with such a strong indicator here, we're going to conclude without really much of a doubt that indeed our mean has changed and it is no longer equal to 12.44, okay? So our decision is going to look like this. Okay, so I typed up my conclusion here for you so that you can read it a little bit easier. So since 5.87, you state the test statistic is greater than 1.96, the critical value, and falls in the rejection region. See, it's way over here in the red. You can't see that the red goes that far, but I promise you the red goes that far. I will reject the null hypothesis that the population mean length of long distance calls for the TIV telephone company customers is currently 12.44 minutes, and I will conclude that the mean length of the calls has changed. I cannot say that it has increased. I can simply say that it changed because that's what my test was for. My test was for change only. The data at a 5% significant level, list that, suggests that the mean time has increased. It just suggests that. I can't conclude that that has actually happened. Alrighty, on to the next question. According to the National Association of Realtors, the mean sale price of existing single-family homes in the United States was $130,000 in 1992. A random sample of 500 such homes were recently sold, gave a mean sales price of $137,670. Use the population standard deviation of $23,700 to test at a 1% significant level if the current mean sale price of such homes is greater than $130,000. Okay, so let's gather our information that we know. We know that in the past, in 1992, mu was equal to $130,000. We took a sample of 500, n equals 500, and we found from that there was a mean price of $137,670. So that X bar is equal to 137,670. Our population standard deviation, sigma, is equal to 23,700. It says test at a significant level of 1%, which means that alpha is equal to 0.01, or that I want to be 99% confident of my results, okay? My confidence coefficient is direct relationship with our alpha. Use this level to test if the current mean sales price of such homes is greater. That tells me that it is a one-tailed test. So it says state the null in the alternative hypothesis. So as I said before, I like to start with my alternative first because it says test if mu is greater than $130,000. My null is going to be the opposite, less than or equal to $130,000. Or you could write it as mu is equal to 130,000. Either one of those is perfectly acceptable. Okay, what am I testing? That mu has increased. It says select the distribution to use. I have sigma. So since sigma is known, I'm using the standard normal distribution, which is the z distribution. Okay, the next thing it says, determine our critical value. Our critical value, again, let's go ahead and draw our picture first. We've got a right tail test. The reason I know it's a right tail test is because I have a greater than sign. So the generalized picture will look like this. I will draw my standard normal distribution, put 0 in the center to represent our mean. We're going to put our z star right here on the right hand side, and we're going to put all of alpha right in here at 0.01. It's all of alpha right in there, and this is our reject. And right in here is our fail to reject. So we'll highlight all of this green. Get out your colored pencils and highlight. And then here's your rejection area right here to the right. And now we need to determine our critical value. What does z star actually equal? Remember that if I have 0.01 here, that tells me that I have 0.99 in here underneath the tail to the left. Okay, so I can go grab my z table right here, and we're going to look for 0.99. Come in here, 0.99, and here is about the closest that we're going to get to 0.99, which is 2.33. If I keep scrolling up, you'll see that that's a 3. Okay, so it's going to be 2.33 is the number you're going to use. 2.33 has 0.99% of the area to the left. So our critical value is 2.33. 2.33. So right here for step 3, we're going to write 2.33. So we have step 1, 2, 3, 4 done. Now we need to calculate the test statistic. So z is going to be equal to, let's look at our numbers up here. It's going to be 137,670. So 137,670 minus 130,000 minus 130,000 divided by our standard deviation, which is 23,700. 23,700 divided by the square root of n, and in this case n was, I know I wrote it down somewhere, thought I did, n is 500, should be right there. I guess it got moved somehow. N equals 500. Not sure how that happened. There we go. Okay, so 500, and that's underneath a radical there. Okay, and we're going to throw this in our calculator, and we find out that it is equal to another very large number, which is 7.24. So again, another very significant number. Way over here, we can't even get it on the graph. Actually, I should have thought ahead and put everything to the left. So way over here to the right somewhere, 7.24, it's going to be right in here, and it's way over to the right. So if we plot it, you can see that we are in the reject. We are not in the fail to reject at all. We are over here in the red, and so we will reject the null hypothesis and conclude the alternative. And this time we can conclude that there has been an increase because we did test for an increase. So I'll take a moment and type up our conclusion. Okay, so here's what I would write up. Since 7.24 is greater than 2.33, I will reject the null hypothesis with alpha equal to 0.01. It's important that you state what level of significance you did your test at. and conclude that the current mean sale price of existing single-family homes, restate what your hypothesis was in the U.S. is greater than $130,000. Okay, that's what our conclusion would be. Let's go on to our next problem. Because couples are deciding to have fewer children, the family size in the United States has declined continuously during the past few decades. According to the U.S. Bureau of Census, the mean family size was 3.16 in 1992. A researcher wants to check if the current mean family size is less than 3.16. A sample of 900 families was taken this year by the researchers, produced a mean family size of 3.13. So that is the sample mean. Use the population standard deviation of 0.7, using a 0.025 significant level, can we conclude that the mean family size has declined since 1992? Okay, so let's go through and gather all the information that we were given to begin with. It said that traditionally we knew that mu was 3.16. Okay, we want to check to see if it's less. A sample of 900 families, n equals 900, was taken this year, and it produced x bar at 3.13. X bar equals 3.13. Population standard deviation, sigma, is 0.70. Using alpha equal to 0.025. Significant level, can we conclude that the mean family size has declined? So step one, what's our null and our alternative hypothesis? Again, I like to write down all the alternative first. So H1 rather, would be that mu, it says, can we conclude that the mean family size has declined? That's going to be less than 3.16. H0 is going to be the opposite of the other. Oops. 1/6. There we go. Now, select the distribution to use. I have sigma, so therefore it is z. Determine the critical value. It's going to be a one-tailed test. It's going to be in the left tail. So my picture is going to look something like this. I'm going to draw my picture here. We're going to put 0 over here to the left. It's going to be some critical value, z star, and it's going to be negative because it's on the left-hand side of 0. I'm going to put fail to reject over here. Fail to reject over here. I'm going to put my alpha in here, and my alpha level, one-tailed test, is 0.025. So it's going to go 0.025 over here, and this is my rejection zone right here, my reject. And I'm going to highlight that all pink because I can reject in here. If I get my test statistic in here, and over here is my fail to reject. No change can be statistically detected. Okay, so there we go. Now, we were asked to find our critical value. 0.025 is what we're looking for. So we're going to come in here, and we're going to find 0.025, 0.025 right here. So it's negative 1.96, negative 1.96. So we're going to come in here and put negative 1.96 for our critical value. So z star is going to be negative 1.96 equals negative 1.96. So that is going to be our line in the sand. And so if we have 0.025 right here, that means I have 0.975 area in here. So I'm going to be 97.5% confident of my results. Okay. So 97.5% confident of my results. Alrighty, calculate the test statistic is going to be next. So our test statistic T is going to be equal to, remember, it is x bar minus mu divided by sigma divided by the square root of n. And this can be found on your formula sheet. So since we were talking about hypothesis testing, let's go ahead and pull up the formula sheet. Formula sheet right here. And look at that. It's not going to be on page 1. It is not going to be on page 2. It is going to be on page 3 where we start, on page 3 where we start hypothesis testing right here, okay? One sample, that's what we're dealing with right now. Sigma is known. Here is our test statistic, okay? This is our test statistic right here, okay? So that is where that is going to be known. Alrighty. So coming back over here, let's plug this in the calculator. Let's see, we'll write down our values first. We're going to be having, let's see here, it's going to be 3.13 minus 3.16 divided by 0.7 divided by the square root of, I don't remember the sample size, was it 900? Oops. So 3.16, yep, 900. And let me double check my sigma, yep, okay. So 900. So we're going to throw this in our calculator. Turn it on, clear it out, and we're going to say 3.13 minus 3.16, parentheses, divide, open parentheses, 0.7 divided by the square root of 900, come out, parentheses, equals. So it's negative 1.285, so I will make this a negative 1.29. So negative 1.29, negative 1.29, and we're going to plot this. We finally have one that we can actually plot on the scale, and negative 1.29 falls between 0 and negative 1.96, which is right here. So right in here is negative 1.29, and you can see that we fall in the fail to reject area, okay? So we're not going to reject, okay? So we did step 6, we plotted it right there, and we're going to make a decision. So my decision is going to be that I fail to reject the null hypothesis, okay? Doesn't mean I accept the null hypothesis, it simply says I fail to reject it. I don't have enough statistical evidence at this alpha level with this particular current sample to conclude that I can reject the null hypothesis. So all I put down is I fail to reject my null hypothesis. So our decision will be, since negative 1.29 is greater than negative 1.96, I fail to reject so to make our decision, since 1.29, negative 1.29 is greater than negative 1.96, I fail to reject the null hypothesis with an alpha equal to 0.025. Okay, so I am going to pause the video or end our lesson for today here, and we'll pick up with the p-values at the next lecture and cover the t-distribution as well as proportion. And then we'll have one more lecture on hypothesis after that, and then an exam. So I hope everybody's getting ready for their exams. Today was a little bit tougher of a lecture. Please join us on Tuesday, Thursday if you have any questions, or send me an email. I'll talk to you all later. Take care and have a good day. Thanks for watching.